Welcome to our exploration of fractals, mathematical shapes that reveal infinite complexity. Fractals are infinitely complex patterns that exhibit self-similarity across different scales. They have several key properties. They show self-similarity at different scales, are created by repeating simple processes, contain infinite detail as you zoom in, and are often described by recursive mathematical equations. The Mandelbrot set is one of the most famous fractals. It's defined by a simple equation, z subscript n plus 1 equals z subscript n squared plus c. This set consists of complex numbers where iterating this equation doesn't escape to infinity. It creates a distinctive black shape with an elaborate boundary. A key property of the Mandelbrot set is self-similarity. When we zoom into the boundary, we discover miniature copies of the entire set. The Sierpinski triangle starts with a solid triangle. The process involves removing the center triangle and continuing this recursively. With each iteration, the pattern becomes more complex, showing self-similarity at different scales. When we zoom into any part of the Sierpinski triangle, we see a pattern that resembles the whole. The Koch Snowflake begins with an equilateral triangle. In the first iteration, we replace the middle third of each side with two sides of an equilateral triangle. As we continue this process, each straight line is replaced with 4 smaller segments, creating more detail with each iteration. An interesting property of the Koch Snowflake is that it has an infinite perimeter, but encloses a finite area. Like the other fractals, the Koch Snowflake demonstrates self-similarity. Each small section contains the pattern of the whole. All these fractals share common properties that define the essence of fractal geometry. They all demonstrate self-similarity at different scales. They create infinite complexity from simple rules and processes. Many can be described by recursive mathematical equations. And remarkably, fractal patterns appear throughout nature and are used in various technologies. Fractals reveal how simple mathematical rules can create infinite complexity and beauty, bridging mathematics with art and nature. Fractals possess fascinating mathematical properties that make them unique objects in mathematics. The Mandelbrot set is defined by the equation zn plus 1 equals zn squared plus c. Points are colored based on how quickly they escape a boundary, and the set has a fractal dimension between 1 and 2. The Sierpinski triangle has a fractal dimension of approximately 1.585, meaning it's more than a line but less than a plane. The Koch snowflake demonstrates a fascinating property. Its perimeter grows to infinity while its area remains finite. It has a fractal dimension of approximately 1.26. Fractals appear throughout nature and have numerous practical applications across various fields. In nature, fractal patterns can be observed in coastlines, mountain ranges, cloud formations, fern leaves, and even blood vessel networks. In technology, fractals are used in computer graphics to create realistic landscapes, in antenna design to maximize reception in minimal space, and in data compression algorithms. Scientists use fractals in medicine for analyzing irregular heartbeats, in economics for modeling market fluctuations, in biology for understanding growth patterns, and in physics for studying chaotic systems. The infinite complexity of fractals emerging from simple rules makes them both mathematically significant and practically useful across many disciplines.